Welcome to this video. And in this video, we look at the DC bridge circuits. As used in measurement systems. DC bridge circuits as used in measurement systems. Now, basically, bridge circuits are commonly used as variable conversion elements in measurement systems, and they produce an output in form of a voltage level that changes as the measured physical quantity changes. When used as DC bridge circuits, then that means the physical quantity gives an output that changes in terms of resistance, and this physical quantity can then be detected as a varying voltage when connected in a DC bridge circuit configuration. A good example of an application is the strain gauge used for measurement of force or weight. The configuration of the DC bridge circuit is as follows. It has 4 arms. On the first arm, we connect the unknown resistor. On arm 2, we connect a variable resistor. And on the other 2 arms, we connect fixed value resistors. These are the 4 arms, A, B, C, and D. So this is the unknown resistance. This is a variable resistor, and these 2 are fixed value resistors. Between points A and C, we connect the DC source. And then the output is taken across points D and B. For the DC bridge circuit, we connect a very high sensitive galvanometer that is able to detect small values of current or voltage. The operation of the DC bridge circuit is as follows. The variable resistance is varied until the potential difference between point D and B is 0. At that point, then no deflection will be noted on the deflection type galvanometer used in the DC bridge circuit. If that happens, then we can notice that a current I1 flows in this network and the current I2 flows here, then flows here as I4 and flows here as I3. At balance condition, I1 will be equal to I4 because no current flows through the galvanometer, and also I2 will be equal to I3. The potential difference between point A and D, that is the drop across resistor RU, will be equal to the drop across RV, and therefore we can write I1 RU will be equal to I2 RV. We call this equation 1. Similarly, the drop across resistor R3, because they share this point and this point, with R2 will be equal to the drop across R2. And therefore, we can write I4 R3 will be equal to I3 R2. Call this equation 2. If we divide equation 1 by equation 2 on both sides, then we can write I1 RU over I4 R3 is equals to I2 RV divided by I3 R2. But at balance condition, I1 is equals to I4 and I2 equals I3. And therefore, these 2 will cancel out, these 2 will cancel out, from which we can make RU the subject of the formula, which will be equal to R3 over R2 multiplied by RV. And this is the value of the unknown resistance as a ratio of the variable resistor. If R2 is chosen to be equal to R3, then we notice that the unknown resistor at that point will be equal to the variable resistor. And this is the use of the null type. This is the null type DC bridge circuit as used in measurement systems, also referred to as the Wheatstone bridge circuit. So this is the null type bridge circuit, and null type because the variation or the resistance, the variable resistance is varied until when no current flows through points D to B, and at that point of the potential difference between point D and B is 0, and at that point then the value of the unknown resistance can be determined as a ratio of the variable resistor. A second type of the DC bridge circuit is what we call the deflection type. The deflection type bridge circuit or DC bridge circuit. The bridge circuit is similar to the previous one, only that in this case we don't have a variable resistor. The bridge circuit has an unknown resistor and fixed value resistor as follows. This is our arm A, our B, our C, and D. We connect again a DC source across point A and C, and then we measure the output across points D and B. So this is the output. This is the input voltage. This is an unknown resistance Ru. You can call this resistor R1, resistor R2, and R3. In this case, then, we don't have a variable resistor, and the unknown resistance can be calculated in terms of the input voltage and the measured output voltage. This circuit can be redrawn as follows. Ru and R3 can be considered to be in series. So this is Ru and this is R3. And similarly, the resistor R1 and R2 are in series, and then they are connected to a common source, Vi. So this point, this is point A, and this is point C. Then these are the points D, where we take our output, and the points B. So this is our output. If we take the voltage at point D to be VA, the voltage at point D to be VA, and the voltage at point B to be VB. So the voltage here is VB, the potential here is VA, then it does mean then the output is the difference between the two, which can be written as VA minus VB. The voltage VA, if you look at it in terms of the resistance R4, Ru, and R3, it is the drop across R3, and by voltage divider theorem, we can write VA as R3 divided by Ru plus R3 multiplied by the input voltage. The voltage VB is also the drop across, this is R1, this is R2, so the drop across the resistor R2, which is R2 over R1 plus R2 multiplied by Vi, from which then we can write our output voltage, which is VA minus VB as R3 over Ru plus R3 Vi minus R2 over R1 plus R3 Vi. We want to make Ru the subject of the formula, and therefore we can write our output over input is equals to R3 over Ru plus R3 minus R2 over R1 plus R2, which is what we had previously. This is R2, R1 plus R2. This is Ru plus R3. Then we can put these under common LCM, or we can write V out over Vi plus R2 over R1 plus R2 will be equal to R3 over Ru plus R3. Put these under common LCM, can write Vi into R1 plus R2 will be V out into R1 plus R2 plus R2 Vi, which is equals to R3 over Ru plus R3. If you take reciprocals on both sides, then we can write Ru plus R3 over R3 is equals to Vi into R1 plus R2 divided by V out into R1 plus R2 plus R2 Vi. If we make Ru the subject of the formula, then it will be Vi into R1 plus R2 divided by V out into R1 plus R2 plus R2 Vi multiplied by R3. You multiply both sides by R3 and then you subtract R3. And this becomes the value of the unknown resistor. In terms of the fixed value resistances R1, R2, and R3, and also in terms of the input voltage and output voltage Vi and V out respectively. And through these, then we can be able to measure the unknown resistance using the deflection type DC bridge circuits. Those are the two bridge circuits that are used in measurement of unknown resistances as DC bridge circuits. The first one, the null type DC bridge circuit. The second one, the deflection type DC bridge circuit. And that is the end of my presentation. Thank you for watching this video.